Hi, I'm Chem's best friend. If you need chemistry help, the information is on the bottom of your screen. So hello, welcome back. Let's learn about Hess's law today. It's an energy chapter, so we are calculating enthalpy, delta H, and how do we do that? Let's go to my screen. Enthalpy is a state function. What's a state function? Well, it's a property of a system that depends only on the current state of a system, not on the path taken. Here is the important part. It's not on the path taken. So in simpler terms, it doesn't matter how the system got to its current condition, only what the condition is. So all it matters is initial and final states. This is really, really great for us, and I'll show you in a second why. So let's explain what a state function is a little bit better. And here is two scenarios, and here is you on the bottom of a very big mountain. Here is scenario 2. Here is you too on the bottom of a same mountain. In scenario 1, you decide to climb to the top of a mountain and you took the scenic route. You did not have very steep climb, you just had to do a lot of zigzags. In scenario 2, you said, just going to go to the top as fast as I can, and you went straight up to the top of a mountain. Well, let's talk about the distance you traveled. The distance traveled in scenario A and in scenario B. Well, is it the same? No, it's not. In scenario A, you walked way more steps. Well, distance traveled depends on the path you took. So it's not a state function. Let's talk about the change in altitude. Does it really matter how you got there? No, it does not matter how you got there. You started here, you ended up here, so many meters higher. Same thing here, you started same and you ended here. Well, so it does not depend on path taken, so it is a state function. So change of altitude is a state function. Is this making things a little bit clearer? Okay. So why would we care about state functions? Well, enthalpy is a state function, which is great. Because what if I ask you to calculate enthalpy of this reaction, of combustion of magnesium? So if you ever saw it in a lab, magnesium ribbon, silvery ribbon, and if you ignite it, lots of heat, light is released. And if I ask you, okay, well, how much heat is released? How will you do that? Do you build some kind of a balloon and try to catch that heat? What about the light released? What about all of this stuff? You realize it's too hard. It's just too hard. But this reaction, actually this question, is in many high school labs to calculate enthalpy of this reaction. Because you cannot do it in one step. You have to break it up in a series of steps. So how are we going to do this? Oh, and I put this number down here from the back of a textbook, from the, appendix. So this is the number, this is actually the real number, but let's say we don't know. So here is the idea of Hess's law. Let's talk about the idea. Here is my reaction. We have my reactants, A plus B plus C goes to D, and we say, what's the enthalpy? Well, in one case, we can do this. Here is what we will be doing in one case. So let's say in first step, we can do in a series of steps, right? A and B react to form to form X. And that absorbs 5 kilojoules. So here is A plus B react to form X, and it absorbs, goes up, 5 kilojoules. Then X and C combine to form D, and that releases 12 kilojoules. So X and C combine to release 12 kilojoules to form D. If I add this overall, if I add these two reactions, you can see that X is here, I can cross it out, and I'm going to wind up with A plus B plus C goes to D, and I'm going to add up these numbers where I had to go 5 units up and 12 units down. Overall, I had to go down 7 units, right? So 7 kilojoules is released. So I can break this reaction in this scenario in a series of steps, and it will be the same as if I did it in one step. So that's Hess's law idea. All right? Okay. So many times this reaction is, students are asked to break it up into 3 parts. So first reaction that we can do in a lab is we can put magnesium metal into a calorimeter, yes, with some hydrochloric acid, and you will see bubbles produced, and you will have a solution of magnesium chloride. And let's say we did some calculations and we say that enthalpy for this reaction in a lab is this. It's not exactly that number, but let's just say this is our lab data, that we calculate the delta H for this reaction. Second reaction is you can actually put magnesium oxide into hydrochloric acid, and you will again be making water here and magnesium chloride. And this reaction, double replacement reaction. Yes, the top one is single replacement, the bottom one is double replacement. And here is, you calculate based on your lab data, that here is the enthalpy for this reaction. Okay, now you also can look up that hydrogen gas can react with oxygen gas to form water. And this number you can look up in the back of your textbook. And this is, enthalpy for this reaction for formation of water is then negative 285.8 kilojoules per mole. So you have these three reactions. So we're going to do is right here. I rewrote them quickly. I just rewrote them with the same numbers. So that's all I did. And then we're going to rearrange it. We're going to rearrange it in such a way that we get the overall reaction. So have a look here. So what I did is I just rewrote reaction 1, right? Reaction 1 was just rewritten and just put down here. Reaction 2 was flipped. And you say, why did I flip reaction 2? Because remember, what's my overall reaction that I'm looking for? It was, let's write this down, magnesium metal reacting with oxygen, right, to make magnesium oxide. So I need magnesium on this side, yes, and I need magnesium oxide to be my product. And magnesium oxide was the only, magnesium oxide was written only one time here, and it was a reactant in my reaction 2, so I have to flip it, right? And then I have hydrogen here as a product. I need to have hydrogen as a reactant for it to cross out. So let's try to actually do this. So I'm going to make this a little bit lighter blue. Let's do this. So I have, here is hydrogen. Let's erase that. Let's, get rid of that. I have magnesium chloride solution. Here is my magnesium chloride. Yes. I have 2HCl. It's going to, yes, go. And I have H2O liquid, yes. So what do I have left over? Let's see what I have left over. What do I have? I have magnesium solid is left over here. I have oxygen left over here. And I have magnesium oxide left over. So if I just add that together, rewrite it, yes. So I'm going to have magnesium solid plus 1/2 O2. Now what's 1/2 O2? That's O, right? It's just oxygen doesn't exist as single atom. And I'm going to have then MgO solid. And if I'm going to just add up the reactions, guess what? I also just added up these numbers written. So reaction 1 was just rewritten. The number is just rewritten. If reaction 2 was flipped, guess what? My sign has to be flipped, yes? And reaction 3 was rewritten, and when I added them, if I add them, I just have to add the numbers, and here it is. So it's not exactly 601 what the back of my textbook did, but remember this was done in a lab. There was, not perfect insulated conditions, so there's some percent error here. But this is pretty good. So Are you ready to actually, yes, and this is just really, really fast. So this reaction here as written, I just wanted to let you know that this is written kilojoules per mole, and this is, that means per 1 mole, yes. And here it's per 2 moles. So this reaction, if we wanted to just say this reaction here, we would have to double this number, right? But usually it will be per mole, which is per 1 mole. So this is still the same number. Do you see what I'm talking about? I hope so. And because if you divide everything here, this 1 by 2, you will have 1, 1/2, 1, and this will be then per mole. This will be this number. Okay, let's actually throw in a problem in there, something totally different. Let's go here. Let's calculate delta H for this reaction and for P for this reaction. Here is my delta H. I want to know what it is for this reaction, and we're going to be given this. So here it's synthesis reaction, right? We're taking carbon, combining it with hydrogen to make pentane. So it's a synthesis reaction, and we are given these 3 reactions. And here is the enthalpy for each individual steps. And the question is, how can we figure out overall? So I rewrote this really fast, and let's see what we can do. Okay, let's look. So I'm going to just think out loud. I see carbon as my reactant, just plain carbon on its own. So I'm going to quickly scan all the products and reactants and see if I see just carbon. Oh, I do see carbon right there. Right there. But this has to be 5C, and I only see 1C here. So reaction number 2 has to be multiplied by 5. Do you see that? So I'm going to just write here. I'm going to do my little, should I try to squeeze it in or go to the new page? Well, so reaction number 2 will have to be multiplied by 5, and then I'm going to rewrite on a new page. I'm going to also just quickly see, do I see only hydrogen? Oh, let's write this down. So reaction 1, we will have to multiply by 5. So this will be times 5. Okay. I also see hydrogen, just diatomic, yes. And I look at my reactants and products quickly to see if I see hydrogen. Here it is. But this is 6 moles of hydrogen. This is 2 moles of hydrogen. What do I need to do with reaction 3? Well, it is a reactant here, and it is a reactant here. That's great. I don't need to flip anything, but I will have to multiply by 3. So reaction 3, I'm going to have to multiply by 3. Okay, let's go here. Do I see pentane anywhere? And pentane is here, but pentane is a product of my original reaction that I'm trying to find out, but it's a reactant here. So if this will be a product, I will need to then flip the sign. So what do I need to do with this reaction? Reaction 1, I'm going to flip it. So flip reaction 1, reaction 2 stays, but I will have to just multiply everything by 5. And reaction 3, again, reactants product stay, but I will have to multiply it by 3. And then I'm going to add things together and see what I get. So let's rewrite this all and see what we get. Here we go. So reaction 1, remember, we're going to do flip reaction 1. So here it is. So we will have then 5 CO2 gas plus 6 H2O gas, and this will make C5 H12 liquid plus 8 O2 gas. And if we just flip it there, we're going to just flip the sign. So delta H is now positive 3,244.8 kilojoules. All right, reaction 2. Reaction 2, remember we have to multiply by 5. So let's do that. So we will have 5 carbon solid plus 5 oxygen gas goes to 5 CO2 gas, and in entropy then we have to multiply by 5, negative 1967.5 kilojoules. And then remember reaction 3, we said we will multiply by 3. So let's do this. So we will have 6 H2 gas plus 3 O2 gas going to 6 H2O gas. So now the entropy of the original reaction also has to be multiplied by 3. This will be negative 1450.5 kilojoules. All right, let's see if we can just add it up and where we end up. All right. So I'm going to quickly start crossing things out a little bit. So I want carbon, yes, combining with hydrogen, yes, and it made this. So let's see if everything else crosses out. Green. I have 5 carbon dioxides crosses out nicely. 6 water crosses out nicely. And here I have 8 oxygens, and 8 oxygens crosses out beautifully, and I'm left only with highlighted reactants and products. So this is beautiful. So I'm going to have 5 carbons plus 6 molecules of hydrogen, making pentane, 1 molecule of pentane. And then I'm going to add up just all the enthalpies, yes? Because I overall added up everything. I'm adding up all the enthalpies. And when I add up all the enthalpies, I'm going to have negative 173.2 kilojoules. And there you go. So let's quickly wrap up. So how do you calculate enthalpy of reactions? There is actually 3 ways, right? Number 1, you can go and do a lab, which will be using calorimetry. Number 2 is you're going to let somebody else do some experiments, and you will find the numbers and use Hess's law and find out, do the experiment in steps, find out Hess's law. But there is a third way. There's a third way of actually doing it. And what's the third way? That will be in my next video. So thanks for watching, and see you next time.